What we're going to do this afternoon is routing protocols, dynamic routing protocols, and RIP, again, is the ICND1 protocol. It's a distance vector protocol. We have two types, distance vector and link state. And link state's definition, I really love the definition of it's the state of the links. What they do is to build the link state protocols do, is to build a picture of the entire network, and they calculate what it's going to cost to get from one point to the other. We talked about the metrics that they use. RIP uses a hop count metric. And to kind of demonstrate that, let me just get a blank slide in here that I can scroll on a little bit. So what we have with a distance vector protocol, it's a distance and a direction. So if we had something like, let's see, we have a router here, a router here. Oh, let's put two routers here, a router here. Let's put one router here. Let me make this a little bit bigger. And we connect these things together with whatever speed. Actually, let's make them some really distant speed. Let's make this 10 gig and make this 10 gig and make this 10 gig. Seems like the logical way to go. Let's make this 56K and let's make this 56K. RIP uses hop count, which is the number of routers between here and there. So instead of picking what you and I would pick, it goes this way, because the hop count to get to this is 1, 2. So a hop count of 2, and this one, the hop count is 1, 2, 3. So the hop count of 2 beats, obviously, the hop count of 3. Distance vector goes a distance, a vector. What these guys do is they have networks attached to them. We'll do a demo here in a second. Networks attached to them. He tells this router A here tells router B, hey, I know how to get to all of the networks that are attached to me. Tells router C that. So he will then advertise it to the next guy and add 1 to the hop count. So we're going to add 1 to the hop count, and we'll look at maybe some debug and see what that looks like. Same thing happens here. So when we get to here, we have a situation that, hey, it's going to cost me 3 hops in this direction, 2 hops in this direction. I'm going to take the lower of the 2, which is going to be the 3 hops for this. So back to this slide. 4 basic components: the routing update process, the RIP routing metrics, routing stability, and routing timers. RIP itself. And we're going to talk about timers. RIP's got a lot of timers in order to prevent routing loops, so that we are not just sending stuff around and around and around in circles, and that it picks based on its definition of efficiency, the most efficient networks. Exchange for information within an autonomous system, an AS, an autonomous system. Another new term, autonomous system of a small network. An autonomous system means that we own everything in it. LeaderQuest, the places where you are, LeaderQuest, Jacksonville, LeaderQuest, Dallas, the autonomous system is there. That we own the wiring, we own the media, we own the resources themselves. We have absolute control of it. So autonomous system is within an area of management, really. Implements a limit on the number of hops allowed in the source and destination paths to prevent looping. We define infinity with RIP, and infinity with RIP is 16. So when we say small network, we really mean small network. The maximum hop count, the maximum number of hops between the maximum number of hops, any place in the network is 15. If we get 16 becomes infinity, and it can't go any further. Implements split horizon, route poisoning, and hold down mechanisms. These are things that we'll look at, but simply put, Uh, Split Horizon says that you can't send information back the route that it came from. So if somebody tells me a secret, I can't tell it back to them. If this guy tells me a route, I can't give it back to them. Why is that? Because if something went down, let's say that he has told me about this network here, it goes down. Before that information can be updated, I need to get there, and I don't know where it is. And so, well, actually, we've done this, and let's go this way. We send it this way. And this fellow says, hey, I know how to get there, but we told him what the path was, so he can't tell us back. So Split Horizon, you can't send information back on the interface, the physical interface that you received it on. That can cause some issues in some protocols, Frame Relay, for instance, which is a protocol, relatively old protocol that's going away, but it used sub-interfaces, and we'll use sub-interfaces a little bit later this afternoon, which means that we can have more than one IP address on a physical interface. So if we had something like this, and we, instead of having multiple interfaces here, these guys all went to the same physical interface, and we have routes here, and we send our route to the hub router here. It can't send them back to this fella because Split Horizon prevents that. Sometimes you need to turn it off to accommodate what's going on at the moment or at any particular configuration. Route poisoning is a special technique to tell everybody that, hey, this route is down. It's no longer available. And what it does is sets a hop count to 16. A hop count of 16, Infinity can't get there. Hold down mechanisms, we have to wait. If a route goes down, route's no good anymore. We have to wait a certain minimum amount of time before we can accept a new route. So to prevent, all of those are to prevent the incorrect routing information from being propagated. The message format, and I think probably one of the easiest things to look at, we'll look at this. We have two types of RIP V1 and RIP V2. V1 is the older version, obviously. And the properties over here, the RIP V1 message format consists of the command version, family, network address, distance address. RIP V1 uses class full addressing. We cannot subnet it. It uses the class full. And you say, well, that's a big deal. And it kind of is a big deal, but keep in mind, it's kind of like a summarization. If we had something here and we had a device over here that's maybe a 10 dot something another, 10.60.10 or a 10.60, 10.60.10.0 network or 10.60 network. Let's say it's a 10. We'll get there. It's 10.60.0.0 network. We could have the 10.60.10 network, the 10.60.20 network, the 10.60.30 on down the line, because the route would go to the 10.60 network. So we could actually have on the individual router, it consolidates the routes that's going to be sent to. And again, depending on how you set it up, how you do your network, different things can happen here. Multicasting and encapsulation. RIP is a broadcast protocol, and RIP broadcasts updates every 30 seconds, and that's pretty fast. Not real fast in networking. So that if we have, again, a bad drawing here, we have a number of routers, and let's say that we want to say something down. Let's add a route here. So 30 seconds, we update router 2. It then tells us, let's go 1, 2, 3, 4. We update router 2, so it adds 1 to the hop count for the metric. And 30 seconds later, it tells router 3. Router 3 adds 1 to the metric, and then 30 seconds later, it sends to router 4. So 30, 60, 90. By the time it gets to router 4, we're talking a minute and a half. A minute and a half is an eternity in networking, as most of you know. So Yes, it does that. Does the updates every 30 seconds. Some of the older ones were even slower than that when we do those things. RIP v2, a little bit improved. In addition to the v1 fields, has 3 new fields: the route tag, the subnet mask, which means that it is now a classless protocol. We can subnet it. Subnet mask, the next hop address. RIP v2 uses classless addressing, and it is a multicast protocol, which means that it's still sending a lot of traffic, but it's sending it only to the devices that have RIP v2 on it. That's how we get the subscription. Just to try to look at a little bit of what goes on. Let's see if this will work here for me. So we can debug IP RIP, and hopefully it won't take a lot of time to get some traffic on this. And just when I need it to, there we go. So we have some information here. Received a v2 update from 100 on Fast Ethernet 01, 172.16.00/16, so the 172.16 network, 1 hop away. And we're getting some other updates. So this is, see, RIP v2 tells me the version number. Let's get out of this so that we can just look at these things. And you all, undebug all or no debug, any of those will work for the command to get out of this. So the metric 1, the metric 3, the metrics here are the number of hops away. So let's see if I rebuild the update entries, 172.16.3, metric of 1, metric of 1. These are all bills sending v2 update, and we're sending it to 224.0.0.9, 224 multicast address via, and I put a number of loopback addresses, virtual interfaces on this thing so that we could have a lot of route sharing so that you get enough information. And when you're building these things, you want to try the protocols out. Interface, LO, loopback, and then give it an IP address is a handy way to be able to build a lot of a big network without actually having to go in and put a lot of interfaces on a device. And I'm just looking to see if it actually earlier had some that had a number of increments in it. This is just, I didn't let it go long enough to actually receive, and to be able to add things to it. Actually, I guess, well, we can go back up here. We didn't show the IP route, did we? When we look at this thing, when we look at these, so the traffic itself shares RIP v1, RIP v2. This is v2, the v2 version, a little bit different than the version 1. The Cisco implementation of version 2 supports authentication so that we're not taking information or not taking routes from somebody we don't know. If somebody were able to get into our network without the authentication, they could just start exchanging information with us and could give us bad routes, could give different routes that we don't want to send somewhere. And you know, a static route, we talked about a little bit about administrative distance, RIP. Got a RIP route, somebody has got into our network and give us a RIP route, but they could do a static route and do the redistribution command, which says, hey, RIP, take this static route and send us a route that we don't want to use. Send us through some location, you know, hacked or whatever else that we're doing with these things. Supports automatic route summarization by default. And the route summarization is if we are subnetted, it will automatically summarize to the class full boundary, the ABC class full boundary. And what does that do? It saves space in the route table. So instead of having to have a route to each individual subnet, we can group them together, much like when I showed the 10.60, all the 10.60 traffic went to that one router. Much like I talked about where I used to work, that we were 10.60 and then we broke them up into class C's, 255, 255, 255, but the headquarters activity to send us traffic would send everything that started with 10.60. It summarized what was going on. Software summarizes subprefixes to the classful network boundary when classful network boundaries are crossed with these things. 3 processes used in building and maintaining a route table in a Cisco router. And the various processes run on the network protocols such as EIGRP, the Cisco proprietary Enhanced Interior Gateway Routing Protocol. BGP is Border Gateway Protocol. BGP is the only exterior protocol meaning running outside of our organization, outside of our autonomous system. It is the protocol that is used on the internet to keep the internet route tables up to date. ISIS is one of those protocols. It's not an objective in ICND1, ICND2, or any of the CCNAs. OSPF is Open Shortest Path First is a standard. It's not a proprietary, unlike EIGRP. The routing table itself, which accepts information from the routing processes and replies to the request for information from the forwarding processes. So we do those things. The forwarding processes request information from the routing table to use that information to make packet forwarding decisions. So what all this is saying is that we're building a route table, we're sharing information. The different routing protocols use a little bit different process, they use different language, they use different algorithms, different priorities to select those tables. The table here is talking about RIP. So in this thing, we're going in this direction, obviously, with the update. This guy says, hey, B, I know about network 1, 2, 3, and 4. 1 here is connected to him, actually 4 on Ethernet 1. 4 is connected to him, 3 is connected to him. He got the information about 2 and 1 from B, so it went this way. So Split Horizon is going to prevent him from sending that information back from router B from actually accepting it. So what B says is, yes, I added network 4 and sent an update to 8. So 4 here, go down here, 4 had a hop count of 0. We add 4 down here, it has a hop count of 1. Every time that we go from one to the other, we have to tell the next guy, hey, it's a little bit farther away, a little bit farther away, a little bit farther away. But you notice that it didn't take the information about 1 and 2, which it got from back here. So 1 and 2 got sent in this direction. Split Horizon says, you're trying to tell me what I told you, and I'm not going to accept it. He already knows about 3 because it's directly connected. So we have a hop count of 0 for the directly connected ones. It then sends the information about 4 to router A. Yeah, I got the update about network 4, adds network 4, adds 1 to the hop count. So we now say that we are 1, 2 hops away from the 4 network, from the 4.0.0.0 network. So sharing information, and they keep doing this. RIP v2 obviously is multicast. RIP v1 broadcasts its entire route table every 30 seconds. So and one of the things that we have been trying to do, as you recall, is to eliminate or reduce the number of broadcast messages that we have in the network. Prefix length, we talked about this with subnetting. Shorthand way of expressing a subnet mask, the forward slash. The forward slash number is however many ones are in the subnet mask. Represents the leading binary bits in the subnet mask in a position of 0. So if we had the forward slash in this one, 255.0.0.0, forward slash 8, and 255.255, forward slash 16, forward slash 24. It is a shortcut way to do that. When you look at the route table, they show up in this format. When you do configuration, you have to write out the subnet mask, 255, 255.0 or whatever mask happens to be for that one. The address identifies the network and which portion of the address identifies the node. We know that about the subnet mask. Tells us how much of the address is network and how much of the address is host. Used by the router to learn about the network type to which the packet must be sent. So we have the ability and shortcut, but not in the configuration to use these shortcuts. The next hop is what we would use in static routes. You can specify the next hop address. We looked at that a little bit. We can specify the IP address of the next hop. Next hop is the device that it's connected directly to. But we can also use, and this one is kind of a little odd, I think, but maybe not. This is an indirect, which says here, which is not directly connected. So what we have here is IP route 10.12.0.0, 10.12 network, 255.255.0.0 goes to 10.15.0.3 goes to this interface, the not directly connected. But we also have to have an IP route to the 10.15 network. So we can do the indirect, but we still have to do a route to get to the indirect interface. Otherwise, this guy wouldn't know where to go. Say, okay, the next hop is 10.15.0.3, the 0.3. I don't know how to get there until I put an entry in the route table. And so I get to the 10.15 network, and you see that this one is with a 252. And the 252, it leaves us 2 bits. This is the efficient way, 2 bits for host, the efficient way to utilize addressing. And that means that we have our broadcast, which we need, the 0.0, and then we have the 2 usable addresses, 0.1, 1.0, and then we have our broadcast address. So 0, 1, 2, and 3. Broadcast address 3, network address 0, usable addresses 1 and 2. Efficient use, subnetting efficient use, because instead of using a whole class C, or in this case a class A, which we really wouldn't do, network, we can break it down into much smaller segments and only use what we need. So the static route next hops during the data forwarding. The next hops are recursively used in the unicast routing table to identify the corresponding directly attached next hops. A long way, a lot of words to say exactly what we said. We give it an indirect route here, not usually next hop is going to be the next thing it's connected to it. So we would here normally say IP route 10.12, 10.15 going to the 15 over here, 10.15.0.0, the next hop address would be 10.11.0.2. And then we would have the same entry in here to get to the 10.15 network would be here. Maybe save a little bit of time by doing this indirect, a little bit configuration time, but static routes work well in very small networks. If we get much beyond that, we wind up in a situation that we spend an awful lot of time trying to update everything that goes along. So the routing protocols, and we kind of sort of did and didn't look at this morning, but instead of doing that table, let's go to the router and look at it, and we'll show an IP route. In the show IP route, the table shows up all the time. C, directly connected. It is a connected interface. S, static. I, IGRP. IGRP, Interior Gateway Routing Protocol, is an old Cisco routing protocol. Is not used anymore. R is RIP. M, mobile. B, BGP. The one that we'll use is Enhanced Interior Gateway Routing Protocol, is represented by a D. And a number of reasons why. The algorithm that it uses is actually called dual. So that kind of works out with that. O for OSPF, and then we have here the EX exterior, which means it's not in its autonomous system. It came from a different one. Those autonomous systems are going to work a little differently than the we own everything. We're the administrative control of it when we do those things. And we have those down here that we can see. This is obviously a RIP network. The R is here for the RIP addresses, the network that we're going to, and the possible paths, the possible next hops, as well as the interface that it goes out of to get to that next hop. We have two routes here. We're going to look at, we talked a little bit about the administrative distance this morning, and we're going to look at what they are here in a couple of slides down. But 120 is the administrative distance of RIP. How trustworthy is it? How much should I believe it? And then the metric here is 2, says it's 2 hops away, 1 hop away, directly connected, different things. The static route down here, the default route we looked at. There's also the gateway of last resort is what it's called. If nothing is in the routing table to get it to the destination, it'll use the default route, the route of last resort to get there for it. So the route source identifies how the route was learned by the router. 2 route source codes for the directly connected interfaces. The C code identifies the directly connected, and the L identifies the local route. The local route, let me get back to this thing. The local route here, this is an older router. It doesn't have the L in it, the local route in it. I think that maybe this one will. It doesn't have a lot of, all it's got is connected. I haven't done anything with it yet. So, yeah, the L here, the C is the directly connected. It's the network address with the 24-bit mask. The L, the local route, is the interface it's going to go out of. You notice it has a 32-bit mask. You can see the CIDR notation in the shows here. Again, we can't use that for configuration purposes. We still have to type in the entire IP address, but it uses it as a shortcut when we look at the configuration. So the L's, the local, actually are interfaces. The 32 bits are the, I am masking this thing as an interface. So the L identifies the local route, the interface that it goes out, the interface address for that particular network. Routing table stores the information, directly connected and remote routes, which we have seen in the remote routes with the show IP route, and then the abbreviations, a couple of them in here: S, static route; D, EIGRP, OOSPF, and R, RIP. And these are the ones that you're going to basically see for CCNA. D, EIGRP, part of ICND2. OOSPF, start part of ICND2. R, RIP, part of ICND1 when we do those. Administrative distance, promised you that we would get here, and here we are, is a feature that the router uses in order to select the best path when there are 2 or more different routes to the same destination from 2 different routing protocols. This doesn't mean that if we have 2 routing protocols, only one of them is going to be used. Only one of them is going to be displayed. The best route's going to be displayed. The other one will be there so that if the better routing protocol goes down, then we can still use the routes that are available in the other protocol. Defines the reliability of a protocol. How trustworthy is it? In the table down at the bottom, directly connected 0. You can't get any better than that, that it is directly connected to me. I can read the IP address. I can see the subnet mask. I know what it is. The next one, static route. And as you know, with my typing skills, that might not be the best thing to do, but the way that it's configured, static routes are more trusted than any of the dynamic routing protocols. The next one, internal EIGRP. We have an internal and an external EIGRP. Internal is 90. So of the dynamic routing protocols, it's going to be the most trusted. After that, OSPF 110, RIP 120. Of the, except for the external EIGRP, the internal routing protocols that we use, RIP is the least trusted. It's going to be, kind of a last resort sort of situation that we can use. What's believable, what's usable on these things. First criterion that the router uses to determine which routing protocol to use: if 2 protocols provide route information for the same destination, which one are we going to use? Which one's going to be the most trusted? The lower value wins in this, and hopefully that's pretty obvious from the table there. A measure of trustworthiness of the source of the routing information, and it is only locally significant. It is not part of any of the advertising that goes on with the routers, with the routing itself. The metric are values associated with specific routes and are ranked from the most preferred to the least preferred. The metric is like the hop count. What's the cost to get there? The parameters, the standards are used to determine the metrics vary based on the routing protocols, and each of them is going to be different. OSPF uses a cost which uses the slowest link, the cost of the slowest link from one location to the other. EIGRP uses a hybrid metric, which is a very long number. RIP uses hop count. So each of them has a different way for evaluating the path from one to the other. Optimal path is the path with the lowest metric for any of these protocols, depending on which one that we are using. And again, if we have multiple protocols, the one with the best administrative distance is the one that's going to be used, the one that's displayed in the route table. The others are going to be there, be available if they're needed, but they won't be used. Multiple paths to the same destination, equal metrics, load balancing is available in this. And I'm going to go back to this. I know I keep flipping back and forth in this, but if let's look at show, got to spell it right, IP protocols. The IP protocols on here, routing protocol is RIP, updates every 30 seconds. The next is due in 16 seconds, invalid after 180 seconds. So if we don't get an update in 180 seconds, we're not going to do that. Hold down. How long are we going to wait? 180 seconds. And then it kind of keeps it there. Doesn't use it, but it kind of keeps the route available until it's flushed after 240 seconds, 4 minutes. We got 3 minutes for the update. You know, that again, we're talking eternities in the time in networking terms. Redistributing RIP, which means that's the protocol it's going to use. The default version, send version 2 and receive version 2. Version 1, version 2 are available on these things. So we're sending and receiving version 2 information. The interfaces that are on here, automatic network summarization is in effect. Maximum path. This is the maximum number of equal cost paths that it'll use. This is a configurable number. 4 is the default for this thing. And then which networks are we routing for? The networks that we're telling everybody we know how to get to. Passive interface here, we don't have any. A passive interface says, hey, don't play. Don't participate in the RIP process. Actually, I think it receives but does not send updates for those. If we wanted to run the protocol and then, well, there's a couple of interfaces maybe got going to the ISP that we don't want to send the information out of, we would make that a passive interface. The gateway 4.1, the distance here, the administrative distance, and then the last updates that we have, and then the administrative distance default here is 120. So a little information about, it's available in the show IP protocols about what goes on with it. Let's see, the multiple paths, and that's where we got there. The equal cost load balancing, and jumping back and forth again, we saw some of that here. And if you look at this one, it's pretty obvious we have, as long as these are all gig, this fast Ethernet to fast Ethernet, and then gigabit, and then the serial connection here are going to be the same cost. So we should have, equal paths going up here. And let's see if we do the 192.168.2 network. 192.168.2, sure enough, 120, we have 2 routes. We can go out 100.1 and 4.1 to get there. 2 equal cost paths to the destination. It'll share those. It won't pick one or the other. It'll send some of the traffic in one direction, some of the traffic in the other direction. Makes it a little bit faster, obviously, but this is for equal cost. Unequal cost balancing, if we had, if we didn't have an equal cost to get there, it wouldn't balance those things. Single routing metric, hop count used by RIP. Hop count, which is typically 1, is assigned to each hop, each router between us and the destination. On receipt of the routing update contains a new or changed destination network adds 1 to the metric, saying that, yep, I got this from router 2, and I got to send my information to router 2. It cost him 3 hops to get to the destination. It's going to cost me 4. So because we're adding the 1 router between us and the destination to these things. IP address of the sender is used as the next hop. Who are we going to send it to? We're going to send it to the IP address that we got the information from. This is a table kind of summarizes the multiple protocols that we said are available. RIP-v1, distance vector, EIGRP. EIGRP is considered a hybrid protocol, although it is at its heart a distance vector protocol. And then the link states IS-to-IS, the one that we're concerned about, OSPF, whether they're classless, can we subnet them, and class full, the class full is RIP-v1. V2 allows us to subnet and do the variable length subnet masks that we looked at when we were doing subnetting. Manual route summarization. These things to do route summarization can cause you some issues sometimes. You can turn that off with the no auto summary command when we do those things. And how big of a network are we going to use it on? RIP, small network. Hop count of 15 is the maximum we can go. So we can only use it on small networks. EIGRP, OSPF, and IS-to-IS, large networks, or at least larger networks, which also means that we're going to have a, quote, more capable router. And that means going to have a more expensive router. And then BGP, very large. Very large, think internet large for BGP, the Border Gateway Protocol. The metric, we have a hop count for both of the RIPs, composite for EIGRP, cost for OSPF, and then path attributes for BGP. And then how long does it take to converge? RIP is slow. EIGRP is very fast. EIGRP, if you have an all Cisco, because it's Cisco proprietary, if you have an all Cisco network, that's the way you want to go. OSPF is fast, and then BGP is slow. And BGP, internet, you probably want it to be slow, because how many routers do you think go up and down, or how many interfaces go up and down on the internet any given day? So you don't want the route tables to be too fast to converge. BGP is kind of like the biggest RIP route, biggest and slowest RIP network in the world. Gateway of last resort, we've talked about a little bit, the default router to which unroutable packets must be sent. If the router looks in got the destination, looks in the route table, and there's nothing there, we're going to send it to the gateway of last resort. We don't have any other choice, the default route. If we don't have a default route, a gateway of last resort, and there's nothing in the route table, we're simply going to drop it, throw it away, and send an error message back saying that the route was, the network was unreachable, an ICMP error message back. Software, the Cisco uses the administrative distance and the metric information to determine the default route or the gateway of last resort. The selected default route will appear in the gateway of last resort line right here. And we looked at that a little earlier. We have the static route 192.168.1.2 to network, the 0.0.0.0, 0.0.0.0, yeah. All the 4 of them, the zeros in this case represent any network. So that says that any network, the gateway of last resort, where we're going to send it, the default gateway, is that location. We at least alluded to some of these timers, the types of timers earlier in the little summary at the top there. The update every 30 seconds. Invalid after 180 seconds, 3 minutes. The hold down, 180 seconds, and then the flush timer after 4 minutes. So the more of the text here, the update timer controls the message sending, starts at 30 seconds and decrements. When the count reaches 0, the update message is sent and the timer is reset. So it's going to send the updates every 30 seconds. A route invalid timer controls problems when no update is received within the allotted 180 seconds. The failed route is set to 16, infinity, which means the destination is unreachable. The hold down timer, the time interval in seconds during which routing information about better paths is suppressed. We're not going to take any updates during the hold down timer that look better than the one that we had. Update packet is received, indicates that the route is unreachable. The route enters into a hold down state to do those things. And the flush timer, when the information becomes invalid, the router doesn't purge the route table, but advertises the route with a value of 16, unreachable. And then the route flush timer is set to 240 seconds, 4 minutes. And when it reaches 0, then the route is purged from the route table. So it takes a little bit of time to get rid of one of these routes. A little bit, the summary that goes on these things, the update, how often they get the updates, 180 seconds, invalid, the number of seconds. Since we received the last valid update, once it expires, it goes into hold down, and then hold down after we get done with that flush. So, you know, some amount of time in order to get one of these things out once we stop getting the information that we need. Preventing routing loops, and that's something that we don't want to do, is have routing loops in these things. The split horizon we talked about, minimizing. According to this, the routing updates sent by a particular router should not contain any information about routes already shared. You can't tell me back something that I told you, is what we're really talking about here. Route poison. Advertise a fail route using a special metric called infinity. Poison reverse is the route poison, but it allows us to violate the split horizon rule. So we set it to 16, but we can go back to poison the route in order to make it more efficient. The metric of 15. The passive interface is configured. It does not participate, and this says in OSPF. All of the routing protocols allow the passive interface to be set on this thing. So it's not going to play in the game. And where would you do that? If we're using a routing protocol and then we have an interface that goes to the ISP, we're probably not going to want to send all of our information to the ISP when we do those things. These are just kind of images about what we're talking about here, maybe with the split horizon business. So this one says, you know, sending info about router C down here, about router C from router B. So we're sending it this information. A route is learned about C router and its networks through B router. A router will not send it back to it. This is what split horizon does. We can't send back the information that we got from one of the other devices. It prevents, you know, some issues, and that would be one of the issues would be as we have a network down here and it goes down. That's a good down, huh? DWN, it goes down, and this one knows about, and we'll call it network A since I'm not doing all big numbers, but network A here, and we tell it about it. Before it gets the update here, B says, hey, I can't get there. A would say, hey, I know how to get there, and it sends me back the information. So we would keep trying to send it to something that should be poison, creating at least a sort of a loop in it. Route poison, infinity. It's down, the metric is infinity. The metric for infinity is 16, because that's as far as we're going to be able to go with one of these things. It just marks it as unavailable. The poison reverse here advertise routes with a hop count of 16, faster convergence. Poison reverse takes precedence over split horizon when both are enabled to prevent loops. Poison reverse is enabled by default. possible increased size of the routing messages. So the poison reverse causes router C to advertise, here we go, router C here to advertise the route is unreachable. So it will again overcome the override the split horizon to allow us to get them back, to get the route blocked. Routing table, populated statically defined routes, directly connected routes, discovered by RIP, EIGRP, OSPF, the routing protocols. And the directly connected, not a big deal. Static routes, we type them in. The static route, we need to be able to have the return route, unless we're the end router, of course. And if we're the end router, and let's say we're going to, one of these guys is the ISP, we only have to have one route out, a default route. And they only have, as long as we have our network set up properly, they only have to have one route in, a summary route. Again, if we had, in our network down here, the 10.60.10.0 network, the 10.60.20.0 network, the 10.60.100.0 network, to send information to us, everything that starts with 10.60.0.0/16 gonna go to us. Once we get there, our router then sends it to the specified masked as Class C networks to get there. So we can simplify routing tables or route tables by good IP address assignments, an orderly hierarchical assignment. OSPF requires a hierarchical assignment. Can be populated by these things. The Cisco multi-layer switch, layer 3 switches, run multiple routing protocols in addition to having a static connected. All this is saying is that we can configure a layer 3 switch to route. What it actually does is, we'll call it, and when we look at those, it routes once, it figures out the route table, and then it does switching. That's why they are faster than routers, because they switch in hardware. They switch based on IP addresses instead of MAC addresses when we do those things. So we can have multiples. To make a layer 3 switch, you have to turn on routing, and it's a config T IP routing. And for the ports, if we want to make the individual ports routable ports, we just give the command no switch port. No switch port, put an IP address on it. 2 routes to the same destination are put into the routing table. The one that remains in the routing table is determined the following manner. 2 routes, different network prefix links, then both routes are considered unique. Different subnet masks, different routes. The packet forwarding logic determines which of the 2 to use. The one with the longest prefix, the longest subnet mask, is the one that's going to be used. Multi-layer switches, multiple paths to the same destination from a single routing protocol, the better metric is going to win. If we have multiple routing protocols, the administrative distance is the one that's going to dictate which one of them wins. We have some labs coming up here, the interfaces. What I want to do, I think, quickly before we do that, this guy over here doesn't have any, I don't think, configurations on it. Show IP route. So we have all of our connected stuff. The reason I did the show IP route, and this is RIP version 2, we go into config T, router, R-O-U-T-E-R, RIP, and then version 2. Version 1 and version 2 are different. You can send version 2 will accept version 1 updates, but version 1 won't accept version 2 updates. So this network, we're version 2, I think. After that, we just tell it which networks we want it to tell everybody about. And the reason I did the show IP route, we can see these networks right here. And this one, since it's kind of class full, 10.1.1.0, and then carriage return. It's going based on the address on the interface, and I use the up arrow key to recall a command because we're just going to go 10.2.2.10.2.2.0, and then we can do the network again, 10.3.3.0, to advertise those things. The other thing we have to advertise is the interface that connects us to the other guy. What that does is when we advertise it, network 192.168.4.0, it activates the protocol on that interface and allows it to communicate. Let's see if this may take a few minutes to get stuff. I don't know, we're getting rip routes already. You know, the simulator here will help us out, but we're getting rip routes to the other locations within this autonomous system, the one that we can control, that we have available to us. So with that, we'll go into some labs. I'll put the ones that we're doing on the share screen, and you can work on those.